So the next chapter I'll be introducing is electric potential, and capacitors. Uh, and this is just a continuation of, continuation of electrostatics in general and electromagnetism in general. So these are the topics for this lecture. So electric potential definition, potential difference, electric potential due to a point charge and dipole, conservation of energy in electric field, equipotential surface, and finally capacitors and energy stored in a capacitor. So these are the topics in this. So after doing this chapter, you should be able to answer this question actually: what causes the lightning? You know. So first of all, just like electric, we define an electric field in the previous chapter. We can define now a new quantity called electric potential. It's more abstract, so more mathematics. So electric potential is defined as this actually. Electric potential by definition is defined as the energy stored by a unit discharge. So it's U over Q naught. U is the potential energy stored by a discharge. Q naught is the discharge, and it's the symbol for electric potential is called is V, and its unit is joules per coulomb, and we call volts. So the unit of electric potential is volt. So how do you find the electrical potential energy stored? This is the formula for electric potential energy stored for a discharge, but how do you find that? So then you're going to need some calculus. This is how we proceed. So let's say this is a source charge, this is the charge, and we like to find the electric potential at point P. Electric potential produced by this charge, right, at point P at distance r. So what you need a discharge. First of all, you need to bring that discharge from very far away distance to point P, and during that process you need to find out how much work will be done against this electric field, right? Because you have to provide some energy, because it will try to repel, right? It will try to repel because this is positive, the test charge is also positive, so you have to do the work done actually against this repelling force. And how do you do that? So then we will have to use this calculus integration. So to find the total work done in any case, actually you just do the integration. So you have to do integration from some infinite distance, from reference point infinite distance to the given point r, and the work done is force times dr dot product. So you do this step, right, and you will end up with this work done. So work done will be stored as the potential energy. So work done is the potential energy, electric potential energy. So Q naught over R. And then by definition, right, by definition of electric potential, then electric potential is defined as the electrical potential energy stored by the discharge. So Q naught will cancel out, and then finally you will end up with this formula. So this is the formula for, electric potential energy at the given distance r from the given source charge Q. Okay, and its unit is, remember, volt. Its unit is just volt. So in reality, however, in real life, actually, we don't actually measure the electric potential due to due to a single charge. So absolute electric potential has no practical meaning. So in reality, however, we're going to measure potential difference. We consider one point as reference, so we're going to measure the potential difference between 2 points. That has the more practical meaning. So what is potential difference? Potential difference is the electric potential difference between any 2 points. So delta V is V final minus V initial, and this is all. So it's going to be just Q times delta V. In reality, so you can see the batteries, these batteries provide the potential difference. So battery, if you connect the battery to a, say, capacitor, right? So that produces that adjusts the potential difference. So we can compare electrical and gravitational field because they are very similar. The only difference is gravitational field is very, very weak actually compared to electric field. So something like this. So you have a capacitor, one plate is positive, one plate is negative, and you have electric field in this direction, right? This is the direction of the electric field. Now, what happens if you release a charge, say positive charge? So this positive charge will have velocity in this direction, right? This is the direction of the acceleration. Why? Because the force in this charge will be that way. This will be the force in that, and then this charge will actually accelerate right in the direction of the electric field. This is similar to this. If you drop a mass in gravity or gravitational field, right? We call it F of G, gravitational field. Then it will accelerate, right, with 9.8 meters per second. So this is similar. They behave similar. They are analogy, similar. I'm just showing you an example. So here's the quick question. The electric potential energy is greatest at obviously at A, because when it accelerates, it loses its electric potential energy. So the potential energy will be converted to kinetic energy, and then obviously electric potential will also be greatest at A, right? Because electric potential is just the potential energy per test charge. So similarly opposite. So now you have the same electric field situation due to capacitor. Now if you try to shoot a positive test charge, right, in the opposite to the electric field, so in this direction, so what will happen? Then it will slow down, right, and finally it stops, right? Finally this final velocity becomes zero. So this is something like that. If you throw something up, so because of gravity it will slow down and finally it stops. This is something like that. So then where is the potential energy greatest then in this case? So potential energy is greatest here at B, definitely, right? Because here it has all its energy is potential energy, just like this, right? They are similar. So electric potential will be greatest at B. So then we can solve some problems as a basic problem, so how do you measure the potential difference in real life? So you just need a voltmeter or multimeter, digital multimeter, analog multimeter, right? They measure the potential difference between any 2 points. So if you have so suppose here you have a positive and negative, right, of the battery, say, right, and you just connect the terminal to the digital voltmeter or voltmeter, then it will measure the potential difference, electrical potential difference between two terminals of the battery. So say 9 volt, right? These are some examples, and this is how you measure. So suppose you have a charge. This is a source charge, right? 25 nanocoulomb. So what would be the potential difference between A and B? So by calculation, you just use the formula we just derived. Find the potential at A, find the potential at B, and obviously potential at B will be greater than potential at A because it is closer. And then find the VB minus VA is the potential difference. Or in reality, you can just use this voltmeter or multimeter. So just put your probe at A and B, and it will measure the potential difference directly. This is a direct measurement of potential difference. And so this is the formula we just derived right in the beginning, and it shows that the electric potential of a point charge decreases with distance r, like this, right? And this is a 3D graph actually. If you plot the electric potential, remember is just a scalar number. This is just a scalar number. It's not a vector quantity because it's just a number with volt. At various points around the charge, a single point charge, right? And if you plot a 3D graph, it will look something like that. What happens if you have a dipole? Dipole means you have positive charge and a negative charge, right? If you now collect the data for electric potential, which is the voltage basically, with a voltmeter, right, around a positive and negative terminal, and if you plot a 3D graph like this, it will look something like that, right? Because it's for a dipole, and this is what we're going to do actually in the lab, actually, electric potential lab. And so at any point, the total electric potential due to the system of charge, collection of charge is just the algebraic sum, right? You don't need to worry about the vector sum here. Because why? Because electric potential is a scalar quantity. You just do algebraic summation, plus or minus, plus or minus. If the charge is negative, its potential will be negative. If the charge is positive, its potential will be positive. Just sum them up to find the electric potential at given distance. Okay, so so you don't need to worry about the vector sum, unlike electric field calculation. And this is what we would do actually. So we're gonna map the electric potential due to a dipole using this carbon paper, conducting carbon paper with it has some resistance. So you connect the positive terminal here and negative terminal here, right? It serves as a dipole, positive and negative. And using this probe, which is connected to the digital voltmeter. Then you probe the voltage at all these coordinates around the positive, and then you plot using Excel or any, then you will end up with this kind of graph, as expected. So next is energy conservation. So just like if you throw any mass in gravity, or if you drop any mass in gravity, the total mechanical energy of the mass remains constant. That means the sum of potential and kinetic energy remains constant. Just like that, if a charged particle moves in the direction of in the vicinity of electric field, right? So here is the example. So here, this is the main source charge, right? It produces electric field, right? This is the electric field produced by this source charge, and electric field is a conservative force. Since electric field is central force, electric field is a conservative force field. So say an electron or any negative charge part moves from some initial point to final point. The total mechanical energy of this moving charge, the negative charge, should remain constant. So that means energy should remain constant. This is our main equation. This is the conservation of mechanical energy. U plus K. The only difference is your potential energy is now Q times V. Q is the charge of the test charge, which is this, right? And V is the electric potential at that given distance, right? And K is just 1/2 mv square. So this is going to be our main equation in conservation of energy in electric field. And here are some sample examples. So the next important concept is equipotential lines or equipotential surface. So by definition, it's the line or surface around a source charge, right, system of charge or charge, where the electric potential is constant everywhere, along the line everywhere, right? It's called equipotential lines. And so since the potential is same, right, equal everywhere along the line, any 2 points, so there's no potential difference between any 2 points on the equipotential lines, obviously. So here are some 3 examples. So this is the equipotential lines. This dotted lines circle, dotted lines drawn are the equipotential, whereas the solid lines are the electric field lines here. The 2 things: equipotential lines, electric field vectors lines. So this is the equipotential lines for a point charge, and obviously it becomes a circle, right, or a sphere. For a dipole, these are the equipotential lines. So that means if you measure the potential, electric potential or voltage here or electric potential here, it will be same. So there will be no potential difference. Similarly, if you measure potential here or here, it will be same. So similarly for a parallel plate capacitor, it will be uniform. It will be vertical lines like this. So these are the electric potential equipotential lines, and this is the electric field. So these are some examples of equipotential. So equipotential line is by analogy. Equipotential lines are similar to the elevation graph. So if you go hike a mountain, mountain region, any adventurous hiker should know this actually. These each line are the elevation graph. That means they are the equipotential lines. So each point on this line represents the same height, same elevation, right? Same elevation. So for example, this is at 4,000 meters, 4,000 meters. So here 5,000 meters. So red line are 6,000 meters. So these are the examples of elevation graph. And elevation graph is the equipotential lines. So the only difference is this is in gravity, right? These are the equipotential lines drawn in gravity, and these are the equipotential in equipotential lines in electric field. And one more thing, the electric field vector must be always perpendicular to the equipotential line at any point. Why? Here's the reason. Because here you are shown 3 equipotential lines: 0-volt line, 10-volt line, and 20-volt line. Suppose you move a charged particle, say Q, test charged particle, from one point to other point along the same equipotential line. So since there's no potential difference, right? Since there's no potential difference between any 2 points along the equipotential line, the delta V will be 0. So no work will be done in moving up charged particle from one point to other point along the given equipotential line. So no work done. So that means there's no parallel component of the electric field. There shouldn't be any electric field along this equipotential line. So that means the electric field must be perpendicular to the line. Okay, there shouldn't be any parallel component. There will be only perpendicular component. So that's the reason. And what's the relationship between electric field and potential difference? So this will give you the relationship between electric field and potential difference. So basically it says electric field is basically the potential gradient. So delta V over delta S is called is simply called potential gradient. Okay, if something changes with distance, it's called gradient. So it simply says electric field, right? Electric field vector is simply the negative of the potential gradient. Negative simply means the electric field always goes from higher to lower potential. Electric field always goes from higher means positive side, to negative side. Right? That's the meaning of negative sign here. And in many cases we will just measure the magnitude. So magnitude of the average electric field, right, is just the delta V over delta S. So that's how you measure electric field if you know the potential difference. And these are some examples, right? So here you have non-uniform distribution of electric equipotential lines. So you have more concentration of electrical equipotential lines. So the electric field must be stronger here compared to here. Here you have less concentration of equipotential lines, right? So that means you have a weaker electric field, and the electric field direction, remember, is always go from higher to lower, right? Because this is our higher potential, these equipotential are lower potential. So the more practical examples are, so if you have a pointed end charge, say this is a charge conductor, say it is positively charged, right? And so if you draw the equipotential lines, so these are all equipotential lines. Look at here. So you have huge number of equipotential lines, so high concentration of equipotential lines. That means you have very strong electric field at the pointed end. At the pointed end, you have very strong electric field, and that causes the breakdown, because that causes this strong electric field around a pointed end, causes the ionization of the air molecules. So air molecules around it starts conducting, and it starts breaking down, and this is called coronary discharge, and this is called, and in many practical examples, in your gas petrol engine, you have this sparking plugs, right, is used, and it has also put this pointed in with some gap, and some high voltage is given to this sparking plug, and at the right time it produces spark. See this spark, and that causes, and that actually ignites the fuel system actually here, and that provides the power to the gas engine. And it's basically same thing, right? This cause of this spark is because of intense electric field. And same thing with the lightning. What causes lightning? Well, now you can answer this question, because when the charge is built up in the clouds for various reasons, it produces causes the intense electric field between cloud and the ground, or positive cloud to negative cloud, right? And when the electric field between cloud and ground exceeds 1 million volts per meter, it ionizes the air molecules, and it causes the breakdown, and this happens. This causes the lightning. So lightning is basically the dumping, sudden dumping of the electrical energy due to the intense electric field to the ground, So there are some examples of equipotentials. So as a final topic, we're going to do capacitor and its capacitance, So capacitor is a tiny, electric charge storing device. So basically it's two parallel conductors actually like this, right? And these are all examples of the capacitors. You will see that in many modern circuitry, any circuit consists of this. These are all capacitors. So basically, it's made from two conducting plates, right, separated by some distance. So first, you can charge it. You'll have to charge it. So how do you charge? You just connect the battery, right, to the plates. And what battery just acts as an electrical pump. So it will remove it will remove some of the electrons from one side to the other side. So this like this. It just basically pump electrons, some of the electrons from here to here. And so since this plate loses electrons, it becomes positive charge, and it dumps electrons to the other side. It becomes negative charge, and this process will continue. This will slowly moves electrons from one plate to other plate, and finally, when the potential difference, the voltage between these two plates becomes equal to the voltage of the battery, then the charging process will stop and the capacitor becomes fully charged. You can say the capacitor becomes fully charged. Now even if you remove the battery, the charges remains here, and it itself works as a battery. Okay, so that's how it works. And so capacitors, most of the capacitors are made from thin sheets of metal sheets, separated by some insulators, paper, mica, something like that. And here's the standard symbol, just two parallel plate. This is a symbol for a variable, and this is a symbol for a polarized. Some capacitors are polarized, so one side is negative, one side is positive, And the first relation is this. So the charge on each plate is equal to C times V. So C is called capacitance, which is capacity of the capacitor, and V is the potential difference between two plates. Okay, so that's the relationship of charge and voltage. So Q is CV. It's a very fundamental relationship. So C is called capacitance, and its unit is coulombs per volt, called farad. Okay, so it's called farad from the name of the scientist, Michael Faraday. And 1 farad is actually a very big unit of capacitance, so that's why so smaller units are given for practical problems. So 1 microfarad means 10 to the power -6 farad, 1 nanofarad means 10 to the power -9 farad, and 1 picofarad is 10 to the power -12 farad. And again, we have already done that. So if you have a capacitor, right, one side is positive, one side is negative. Electric field always goes from higher to lower potential, positive to negative side. So how do you find the electric field? So electric field is just the potential gradient, right? We talk about that. So it's delta V over delta S. Delta S is the distance, this distance. So delta S is just, let's say, D. So capacitance depends on many factors, shape and size. So capacitance is also given by this. This is called permittivity. It's a Greek letter epsilon naught, right? It's a permittivity of the medium. A is the area of the plate, and D is the separation between two plates. And the use of, so usually in real life, actually, these capacitors are the two plates of the capacitors are separated by some insulators, and insulators are called dielectric, right? And the use of insulator in between the capacitor actually increases the capacitance. It increases the capacitance. And here's the brief reason, actually, because of polarization, it develops its own charge, opposite charge on each side, and it reduces the effective electric field between these two plates, and eventually it will increase the charge holding capacity. It increases the capacitance. And this is our final relation of the capacitance of any capacitor. So it depends on K. K is called dielectric constant. This is the K. This is the dielectric constant for different materials. Different materials have different dielectric constant. Epsilon naught is always a constant. It's a very small number from the formula sheet called permittivity. A is the area of each plate, and D is the separation between two plates. So these factors, affect the capacitance of the capacitor. So charging a capacitor is something like filling a water tank with the help of a mechanical pump. So here your pump is your battery. Battery is like electrical pump, right? It helps to move electron from one plate to other plate, right? I briefly mentioned that. Just like this, filling a big water tank with the pump. Pump slowly moves water from lower to higher potential, right? fill this up and is fully charged, just like that. And then you can dump this water, right, just opening the valve, just like that. You can dump the charge energy of the capacitor just by shorting it. So when a capacitor is charged, it stores some energy, right? So how do you find that? Then you're going to briefly need again briefly need some calculus. So you just need to integrate. So initially the voltage across the capacitor is 0 before it's charged, and when it is fully charged, let's say V is the voltage, and Q dV is the small work done in adding small amount of charge. So what you need to do is you have to find the total work done. Right, to find the total work done, you have to do integration of the small work done, and you do some step, and you will end up with this. And this work done by the battery stores as the electrical energy, electric potential energy. And this is the formula actually for the energy stored by our charge capacitor. Energy stored, electric potential energy stored in a charge capacitor. 1/2 CV square. C is the capacitance, V is the potential difference or voltage between the two plates. And one more thing, actually, since Q is CV, right? So you can write down the energy stored in a capacitor in many different forms, actually. 1/2 CV square, that's the first formula. Or you can also do U is, Q times V, half Q times V. Or U is also 1/2 Q square over C. So these three formulas, depending on the type of the problem, you can actually use one of these formulas in numerical calculation. And here's an example of quick discharging of a capacitor. Capacitors can dump energy, discharge energy within a fraction of seconds. Unlike battery, battery takes much longer time to discharge, but capacitors can discharge the electrical energy within a fraction of seconds. And it has many applications. And here's an example. If you first you charge the capacitor, right? This is the capacitor, and then if you toss the two positive and negative side, if you short them, if you jump it, if you short this positive and negative terminal, you might get electric spark because of quick discharge. And this quick discharge capacity of a capacitor has many applications, just like the camera flash system, right? You will have, because you will have to dump the electrical energy in the form of light energy within a fraction of seconds. And this is the capacitor shown here. This is the capacitor. And in this heart defibrillator, because in case of heart failure, or heart attack, actually you might have to reactivate the electrical activity of the heart very quickly. So you're going to use these two terminals, right? One is positive one. This is also a capacitor. So here you dump the energy within a fraction of, use the energy within a fraction of a second using capacitors. And there are some examples.